Hey everyone, welcome to our presentation on human population. Up until now, we've been talking about non-human populations and how they grow or shrink or move or evolve. Now we're going to start to talk about human population and human population growth. The study of that, by the way, is called demography. And obviously, the human beings on the planet and the amount of us there are on the planet has really large ecological consequences. So let's get started. So we've talked about the concept of a carrying capacity for non-human species. And if you can remember, the abbreviation for carrying capacity is a capital letter K. So the question is, does Earth have a carrying capacity for humans? Humans are classified as animals. We have a taxonomic category just like all animals do, but this is kind of in debate. So about every 5 days, the human population increases by about 1 million people. Think about that. Every 5 days, there's another 1 million people born on this planet. Until a few hundred years ago, human births and human deaths were essentially equal. So the number of births and deaths canceled each other out. So we did not have a lot of population growth. About 400 years ago, agricultural output, we started farming rather than hunting and gathering. And so agricultural output began to increase and sanitation began to improve. Sanitation means like, getting rid of where you poop and all that stuff. Death rates began to fall at that time, but birth rates remained high. So as less people were dying, we were still having more babies. And this was the beginning of the human population boom. There was a philosopher in the 18th century, Thomas Malthus, and he wrote in 1798 that the human population grows exponentially, which is what we have seen, that it's a J-curve, but our food supply only grows linearly. So if I were to make a graph of that, I'm going to put it right over here. It would look something like this. Get my pen ready. So here's my Y and my X. So human population growth would look like this, right? But our food supply would look like this. So we'd have linear growth. And so there was a point, right about here where those graphs cross, that human population growth and the number of humans would outstrip their food supply, meaning that everybody born after this crossing point would be hunting, be looking around for food and would be starving. This is the dominant model. This Malthus model of scarcity is the dominant model for environmental scientists today. However, there's a lot of evidence that this is not the correct model, that we're thinking about things in the wrong terms. So some social science, now this is environmental scientists. So how about this? We switch from environmental scientists to social scientists. So some social scientists believe that Earth doesn't really have a carrying capacity for humans because we are fundamentally different from other species in the animal kingdom. Our intellect is far and beyond what any other creature demonstrates. So social scientists say that human intellect is always going to lead to innovation in the way that we get food, and that technological advances will increase food production so that we will always be able to feed a growing population. Now, obviously, one can imagine that there's a point, right? This always is kind of problematic, where there just won't be any other way to do it. But there's all kinds of advances in agricultural output and even soilless growth techniques that we'll talk about that can help feed people in non-traditional ways. So what are some things that make the human population grow, factors driving population growth? Well, first off, let's talk about some definitions. I told you that demography was the study of human populations and human population trends. So that's where we really are right now. We're talking about demography. And we have already kind of launched into that because you guys did the cemetery, the survivorship project. And that is actually a study in human demography. How many people die at any given time based on societal factors like, access to modern medicine or sanitation and those kinds of things. And at this point, when you mapped those growth curves, you should have seen a difference. When I'm grading your stuff, I'm really clearly seeing that your type 1 survivorship curve, right? Which, of course, let's do that again on here. So, we got 3 types of survivorship curves, and this is all logarithmic. They look like this, right? And this is a type 3. This is a type 2. And this is a type 1. And humans are a type 1, which means that not many individuals are lost in the beginning, but as age goes on, because this is time along the bottom, more and more individuals are lost as they age, which is a typical type 1 for K species, right? Survivorship curve for K species. And what I was seeing with your cemetery demographics is that your deaths to 1925 did not really resemble this. Some of them resembled a type 3 because in the cemetery that we were in, there was a lot of babies that were there. Which would indicate a type 3 survivorship curve. And then as you moved mid-century, we saw more of a type 2 survivorship curve. And then in your last cohort, it was kind of easing into a type 1 survivorship curve. And we're going to talk about why that is. All right, so populations have inputs and outputs, things that make them grow and things that make them shrink. So the inputs include births and immigration, and you have been introduced to this in some of your worksheets that have been assigned to you. When I gave you those density and distribution worksheets, you've already seen these equations. Outputs, things that make the population shrink, include deaths and emigration. Be real careful when we, right there. Immigration means coming in, emigration means going out. So we have to talk about biotic potential, the biotic potential of a species, which of course is its propensity to grow, R, versus environmental resistance. So biotic potential is, we talked about this just briefly, the potential that a species has to grow given unlimited resources, no limits on resources. That means all the food, all the space, all the water, all the mates, whatever it is, whatever resource they need to grow, that is present in unlimited quantities, which of course we know is not the case in the real world. But this is how we get those R species and K species, right? So species that have a very high intrinsic growth rate with a high biotic potential are going to be R-selected species. Those are things like weeds and bugs and anything that produces lots and lots of offspring and has a very rapid gestation time. Organisms that are K-selected, they have a low biotic potential and a low intrinsic growth rate. Those are K-selected species that even given unlimited resources, they're still not going to produce a lot of offspring. Environmental resistance is what pushes back against biotic potential. So whereas biotic potential is unlimited resources for all time, right, which is hypothetical, it doesn't happen in real life. Environmental resistance is what is pushing back against biotic potential. It is the limitations on those resources that keep the biotic potential from reaching its full capacity. So crude birth rate is the number of births per 1,000 individuals. Remember, if you have the word rate, it's per something. And in this case, it's per 1,000 individuals. And the crude death rate is the same except for death. So birth rate is per 1,000, death rate is per 1,000. So the equation for population growth rate, and again, you've seen this before if you did your density and distribution worksheets, are births plus immigration. Of course, these are our positives, right? Everything that increases a population. Positives. Subtract your deaths and emigration. And these are our negative factors, the things that make population shrink. So births plus immigration minus deaths plus emigration gives you your population growth rate. So we're going to be doing some math work on this concept of doubling time. This is an important concept. The doubling time of a population is the number of years it will take for that population to double in size. The way that this is calculated is we use something called the rule of 70. I'm going to tell you a secret. I didn't know the rule of 70 the first 2 years I taught APES, and boy, was my life hard. And I will also tell you another secret. There are APES teachers who do not know this rule. And it makes their life hard too. But listen to this. So the doubling time in years of any population is 70 divided by the growth rate. Any population. Notice I didn't give you a starting point. So check this out. A population growing at 2% a year. Do I need to know the population starting point? I do not. How long is it going to take it to double? Well, here we go. Here's our math. 70 divided by our growth rate is 35 years. Now notice my growth rate is not converted. It's just 2. I didn't convert it back to a decimal. So this is the number one. This is the number one screw up that kids do on the rule of 70 is they convert their percentage back into decimal. Don't do that. So 70 divided by 2 is for 35 years. So this is true of any population size growing at 2%, regardless of what it started at. So a population of 50,000, let's say we start with 50,000, will increase by 50,000 in 35 years, okay? 35 years, that's our doubling time. It doesn't matter what you start with. If you start with 50,000, you're gonna add 50,000, that's doubled in 35 years. Let's say we start with 50 million. In 35 years, we're gonna have another 50 million, okay? 35 years is the doubling time of any population growing at 2%. And of course, it just depends on the growth rate, right? So if it's 3%, then you do that math, 70 divided by 3. Makes sense? Hopefully. We're going to do a bunch of math practice with this. And this is super, super important. There's always a couple, usually 2, doubling time questions in the multiple choice section of the APES exam. Fertility. Total fertility rate, or TFR, is the average number of children that each woman in a population will bear during her lifetime. Total fertility rate varies by country. It also varies by subgroup, either ethnic or cultural, within a population. Replacement level fertility, or RLF, is the total fertility required to offset the average number of deaths in a population so that the population size remains stable. So let's talk about what this means actually. Every baby on this planet has 2 parents, okay? So replacement level fertility, the minimum it can be for a population for it to be stable is 2, meaning that every baby born has to have 2 babies in order to replace its parents. That would keep a population stable. Now, if there's a lot of people dying in that population for whatever reason, then the replacement level fertility would need to go up in order to keep the population rate stable. Let's say that there's a war that's killing a lot of folks in the population. Replacement level fertility would need to go up in order, like each baby born would have to have 3 or 4 children in order to offset the number of deaths in a population. But if there's not something that's killing people, then the replacement level fertility would be 2, obviously, to replace your parents when they die, to keep the population stable. Populations that have a replacement level fertility of less than 2 are populations that are shrinking in size. Let me say that again. If your replacement level fertility, or your RLF, is below 2, then the population, not accounting for immigration, is declining. So when the total fertility rate is equal to the replacement level fertility rate, and immigration and emigration are equal, then a country's population is stable. So here's the key, right? A lot of countries have a replacement level fertility rate below 2, meaning that the people who live in the country are not having enough children to replace the deaths in the country. But immigration can keep a population growing even if the replacement level fertility is below 2. And this has happened actually in a lot of European countries. They're at 0 growth. And the only reason they're not in declining growth is because they have immigration. They allow people to immigrate. Their replacement level to fertility in many of the European countries has been below the total. The total fertility rate has been below replacement level fertility for many years, and immigration is making up the difference in a lot of those countries. Okay, life expectancy. Again, this is a social science concept, right? Life expectancy is the average number of years that an infant born in a particular country can be expected to live. And notice that it is in a particular country. This is based on the conditions in the country. It's higher in developed nations and lower in less developed nations. It's usually expressed as overall, meaning everyone in the population, and then both male and female. In the US, the life expectancy is 78 years old for overall. It's 75 for men and 81 for women. In most countries, women live longer than men. There's a variety of reasons for that. Some of which are probably biological, and some of which are societal. Men go to war, women usually do not. And men culturally sometimes have the, hey, y'all watch this factor that women don't have. But there's lots of reasons for that. All right. Infant mortality rate, that's the number of deaths of children under 1 year of age per 1,000 live births. Again, right? If we say rate, we've got to be per something. When we're talking about these numbers in demography, it's always per 1,000. So our infant mortality rate is everybody under 1 that dies. The child mortality rate, exactly the same thing, but it's everyone under 5. So this is under 1, this is under 5. Okay. And again, one would expect that infant and child mortality is higher in countries that are less developed and lower in developed countries. If life expectancy is high and infant mortality is low, we'd predict that the country has a high level of healthcare and is a developed country. Sometimes the test asks you to make predictions about the stage of demographic transition or the level of development of a country based on statistics that they give you. And it's important to know how those things go together. Aging and disease. So even with a high life expectancy and a low infant mortality rate, okay, that would mean that the country is developed and has access to modern healthcare. A country may still have a high crude death rate because it has a high proportion of older people. This is true of many countries that have been developed for a long time. Japan, for instance, is what I'm thinking of. They have a very high life expectancy. Japan's life expectancy is one of the highest in the world, and they have a very low infant mortality rate. But they have a higher crude death rate because they have a lot of old people. Japan's an aging country. The biggest killer worldwide is heart disease. So across the world, the number one killer of people is heart disease. The second biggest killer is infectious disease. And of that category, infectious disease, HIV is the number one killer in that category. HIV kills more people across the world. It's the second killer, right? So we've got heart disease first, but that's not infectious disease. Second category is infectious disease. The top one in there is HIV. So across the world, what people are mostly dying of is heart disease and AIDS. Age structure diagrams. You've been introduced to these before, but we're going to talk about them again. Age structure diagrams can be used in non-human populations and they can be used in human populations. They're more common in human demography, but they can be used in non-human populations as well. A population's age structure describes how its members are distributed across age ranges in 5-year increments. Age structure diagrams are visual representation of an age structure within a country for both males and females. They're pyramidal shaped. So if it's a pyramid, like a strong pyramid shaped, meaning a wide base and narrow top, it means that the country has a growing population, and that's generally true of developing nations. If it's a column shaped or more rectangular top to bottom, that would represent that the population is in stability, which would represent an industrialized country. If it's a kite shaped diagram where the top part of the diagram or the older people cohorts are larger than the younger people cohorts, kite shaped, that represents a population that is declining, meaning it's getting smaller, and that would be representative of a post-industrialized country. And some of these words don't mean a whole lot because we haven't talked about demographic transition yet, but they will. Okay, so you guys have seen these briefly before in a previous PowerPoint. These are age structure diagrams, and the different shapes represent countries that are either growing quickly, slow growth, zero growth, or negative growth. So let's kind of go through this. On these age structure diagrams, I'm moving stuff around, hang on. Males are always on the left, females are always on the right. Even if they don't label that, you have to know that. Along the bottom, and this particular graph does not show it, but along the bottom, they would have numbers here so that you would know what scale you're talking about in terms of actual numbers in the population. The three chunks that we kind of chunk things into on these age structure diagrams are pre-reproductive age, which is generally up until the age of 14, reproductive age, which is 15 to 44, and post-reproductive age, which is 45 to 85 and anything beyond that. There's different characteristics of those age groups, right? Not just in terms of reproduction, but in terms of who's going to work, in terms of who's paying taxes and all that other stuff. So there's a lot that can be said about these. Each one of these little stair-step thingies, like each one of these little doohickeys, right, is a 5-year cohort. So the first one would be 0 to 5, and then 6 to 10, and all that good stuff. So when we're talking about infant and child mortality, that would be this first little chunk right here up until the age of 5. Okay, that first stair step on each one of these. It also, you can see it in a rapid growth pyramid that the base of this, the pre-reproductive age, is very, very wide. This means that the folks in this chunk are having lots of babies. Let's move. And you also kind of have to know some countries that are characteristic of rapid growth, slow growth, zero growth. So rapid growth areas would be places that are developing or have a cultural predisposition towards large families. Slow growth would be places that where their replacement level fertility is usually below 2, but they have high rates of immigration. Okay, zero growth would be places that that are highly developed. So let me write developed. And they also have low immigration. And that's why the country is pretty stable. And then negative growth tend to be post-industrial or very, very developed. And also low immigration because the population is declining. So rapid growth pyramids look like a pyramid. Slow growth looks like a narrower pyramid. And again, United States, Australia, Canada, the folks who, when they get here, birth rate falls, but immigration continues to keep the population growing. Zero growth are places, most of Europe is in the zero growth. Denmark, Austria, Italy, they have a low intrinsic rate of growth in their population, and they also don't have a super high rate of immigration. And then negative growth is places that have a aging population. The one that we need to put 2 on here, Japan and Russia are our 2 biggies on here too. Germany, Bulgaria, Hungary, yes, all those are negative growth, but Japan and Russia are also on here, and they're pretty much they're big ones with the negative growth. Those are declining population, negative population growth. Okay, types of population growth. We already know this. So exponential is a J-shaped curve. It represents the biotic potential of a species. I've already talked to you about that. There is a question on the APES exam that asks you which of the following pieces of a graph represents the biotic potential of a species. If you see a J-curve, that's the answer. Biotic potential of a species, species with high intrinsic growth rates also have high biotic potential, so they're going to show a J-shaped curve. This is shown by what we call r-strategists and colonizing populations. Colonizing populations are populations that move into an area, reproduce rapidly, and then die off quickly. So let's take a little closer look at the parts of a J-curve. You've been introduced to the J-curve, but we haven't talked about the parts. So the flat phase right here is called the lag phase. The lag phase is where the growth is not particularly fast because the number of individuals being added to the population per unit of time is actually small at this phase. So we get to a place, which is about right there, where the lag phase stops, and we get that true exponential growth, which is right here, and for the rest of this curve. Okay, so exponential growth is sustained only when there are no constraints from the environment. Remember, biotic potential is limited by environmental resistance. How hard does the environment push back? And then, of course, at the top of a J-curve, that's the number of individuals being added to the population per unit of time is very large. So in the lag phase, it's small. At the top of the J-curve, it's large. And then, of course, during this whole kind of body part of that J, the growth rate is quite high. Obviously, it's exponential, which means it's high, right? Logistic growth is shown as an S curve, and one of the things that we didn't do before was we did not extrapolate. I didn't show you those oscillations. So let's talk about that. An S-shaped curve stabilizes around the carrying capacity, and that is right here on this graph, this dotted line. Logistic curves or S-shaped curves are shown by K-Strategists. So let's take this graph apart here. Again, we have a lag phase, just like we did in the exponential growth phase. And then we have a part of this graph right about here where the growth is exponential or nearly exponential. So if I were to cut off the graph here, you might not be able to tell whether the growth was going to continue as exponential or kind of even out to logistic. But as time goes on, the population encounters resistance. That's the environmental resistance to exponential growth, and begins to stabilize around that carrying capacity. And we have overshoots and we have diebacks, and we have overshoots and diebacks and overshoots and diebacks. And that's what this is right here. So the overshoots are when we go over the carrying capacity. The diebacks are when we fall back underneath, when environmental resistance pushes back. But over time, if you were to take the area under the curves of the overshoot and the area under the curves of the diebacks, you would see that they actually cancel each other out. So if you were to take that average, right, you would end up stabilizing right around the carrying capacity. So at any given time, if you were to look at this population, it might be over the carrying capacity or under the carrying capacity. But if you graphed it over a period of time, it would all even out, and those fluctuations would kind of zero out to the carrying capacity. Okay, K-strategists versus r-strategists. K-strategist species are called competitors. They reproduce late. They have very few offspring, and they have long generation times, which means they stabilize around K. They generally tend to be big-bodied. They live for a long time. They spend little of their energy on reproduction. They tend to do well in competitive conditions where the population is near or at carrying capacity. Unfortunately, K-strategists are also prone to extinction because they are niche specialists. So when something in their niche is no longer there for them, they tend to just go extinct. R-strategist species are opportunists or colonists. They're species with a high intrinsic rate of increase or a high biotic potential. They have many small and unprotected young, and most of these R-strategist species die before reaching reproductive age. So their survivorship curve would be a type 3 survivorship curve. Let me just say that here. So we have a 3 survivorship curve there and a 1 survivorship curve here. Okay, so migration, you guys probably have an idea what this is, right? Regardless of birth and death rates, a country may experience population growth, population stability, or population decline due to migration. We already talked a little bit about how a country can stay stable in their population numbers, even if their replacement level fertility is below 2. And that is due to migration or immigration. So the U.S. is a good example. We have a total fertility rate of right around 2.1, and that fluctuates. So our age structure diagram should look like a column. It should look like a zero growth because we have a TFR that's right around replacement level fertility. But we have a high rate of immigration. So we are actually in the slow growth category because the population that's here, our birth rate is right about, replacement level. We're replacing the people that die, but immigration is making up the difference. So we have a slow population growth rate. Net migration rate is the difference between immigration and emigration in a given year per 1,000 people. Remember that anytime we're talking about demographics, it's per 1,000 in a country. So it's just balancing out how many more people are coming in or going out, and vice versa. Demographic transition is, again, a concept that if you've taken AP Human Geography, you probably have heard about. But if you haven't taken that class, it may be unfamiliar with you. So as a country moves from an agricultural base and a subsistence economy into industrialization and through increased affluence, it undergoes a predictable shift in population growth. We're going to take this graph apart in the next few slides, stage by stage, but just as an overview, generally speaking, countries start off here in the pre-industrial stage, meaning that their economy is based on agricultural work. And in that stage, the birth rate is very high and it's steady. That's the green line. And the death rate is also high, and it fluctuates. The death rate is the kind of the purpley brown line. So let's talk about why the birth rate is high and steady and why the death rate fluctuates. So birth rates and death rates, we told you that prior to about 400 years ago, birth rates and death rates were largely equal. So population growth is very slow because for all the babies that are born, and there's a lot because the birth rate's high, there's also a high death rate. The death rate goes up and down. It fluctuates because since we don't have modern medical care in a lot of these pre-industrial countries, anything that would be like an epidemic or a viral infection, a flu, something like that would kill a large number of people, which would mean that the death rate would go up. And then when those things are not occurring, the death rate would go down. So the fluctuation in death rate that you see in stage 1 right here is characteristic of a pre-industrial economy, one that's based on agriculture. Birth rates and death rates are both high. Birth rates are high and steady. Death rates are high and they fluctuate. Because they are equal, population growth is very slow. So as the country moves through demographic transition, you end up with this next stage, which is stage 2. Birth rates remain high and steady. Okay, so the birth rates haven't changed, right? Okay, but because we have the influx and the development of modern medicine and better sanitation, the death rate is falling. Okay, so everything in purple in this stage, which is all of this area right here, is population increase. So you can see that the population is growing very rapidly here, and there's a high rate of increase because the birth rate is still steady, and yet the death rate is falling. There's a couple of reasons why that birth rate stays high, and we're going to talk about those as we talk about stage 2 a little bit more. As we go into stage 3, the birth rate begins to fall. By the end of stage 3, it's quite low, and the death rate has kind of bottomed out and is low and steady here. And again, population growth is still rapid. It's all this purple area under the curve here, but it is slowing down because birth rates are falling. In stage 4, which is the post-industrial phase, the death rate is low and steady, and the birth rate goes up and down and up and down. So the death rate is now largely kind of bottomed out, and it tends to remain steady because modern medicine has made advances to where people are not dying of epidemics anymore. The birth rate goes up and down based on several factors. One of those can be war. By the way, if you've ever heard of the term baby boomer, societies that are post-industrial have time periods where they have higher birth rates and time periods where they have lower birth rates. Okay, let's talk about each stage individually. So let's look at stage 1 a little bit more closely. Again, I told you that the population growth rate is very slow, and the reason for that is that birth rates and death rates are largely equal. Okay, and again, birth rate is high and steady, death rate is high and fluctuating. This is typical of countries before modernization. They tend to be agriculturally based, meaning that much of their economy is based on farming and agriculture. In stage 2, we have rapid population growth, and the graph is not on here, but I want you to kind of think back to it. The death rates are falling and the birth rates remain high, so the population increases very rapidly. This is true of early industrialization. So let's talk about why death rates fall. Well, we have better sanitation, meaning that people are not putting waste into the streets. You guys know that when people are in contact with human waste, it spreads disease. So when we begin to have modern sanitation with flush toilets and those kinds of things, death rates fall because you're not being exposed to human waste. The drinking water usually becomes cleaner. When we put modern plumbing systems into place, we also do water treatment, which leads to less waterborne diseases. Countries that are industrializing have increased access to food and to goods. Remember that in stage 1, we have an economy that's largely farming or subsistence agriculturally based. But when we move into stage 2, we have the development of markets and cities where we can have access to goods and services. And then, of course, modern medicine is kind of a biggie. So we've improved healthcare, including vaccinations against infectious diseases. Birth rates remain high during this stage, however, because it takes families at least a generation to notice the decline in infant mortality and adjust to it. So people are used to, from stage one, people's culture, they're used to having lots of babies because a lot of babies die. So it takes people a while to recognize that the babies are not dying as much so that they don't have to have as many children. It also takes time to implement educational systems and birth control measures. And I told you that there were several reasons why that birth rate remains high. So if they ask on the exam, it's because it takes a while for families to notice the decline in infant mortality and to adjust to it. It takes time to implement educational systems for children and birth control measures and access to birth control for women of reproductive age. Stage 3 is where we have stabilization of population growth, and this is the late industrial phase. The economy and the educational system are improving. People are having fewer children. Well, why is that? Well, as the populations are moving from subsistence to industrialization, we're going from a rural setting to an urban setting. We have the development of cities. As people move into cities, having a lot of children becomes a financial burden. On a farm, one of the reasons why people have lots of children is because they need a labor force. And in farming communities, children are labor on the farm. But when people move into an urban setting, having lots of children in an urban setting, you just don't have as much space. In an urban setting, children tend to go to school. It's just much more expensive to do that. So having a lot of children becomes a financial burden. Also, when you're in an urban setting, more time is spent. The children have more time spent pursuing education. And the availability of birth control is more widespread. But cultural, societal, and religious norms also play into birth rates. So I mentioned earlier in the presentation that countries have an overall fertility rate. They have an overall crude birth rate. However, subpopulations within a culture, within a country, will have varying birth rates. So you could say, what is the Caucasian birth rate? What is the Hispanic birth rate? What is the African American birth rate? What is the Native American birth rate? Each of our U.S. Census sub-reporting categories would have a different birth rate. And you could even break that out by religion or cultural society. So if you wanted to say Caucasian, but then you wanted to say, people who practice the Mormon faith, that would be a higher birth rate than perhaps the rest of the U.S. Caucasian population. So you can kind of spin that a bunch of different ways. The population is still growing due to population momentum at this stage, but the rate is slowing down. So let's talk about this population momentum. So because we had a lot of babies born in stage 2, there's a lot of people now reaching reproductive age. So the population is still growing, but the rate of growth is slowing down, and that's called population momentum. Stage 3 is considered a steady state. The U.S. is in this stage right now, as is Australia and Canada, places that have immigration. They have a replacement level fertility, which is right around 2. They're slow growth. Stage 4 is declining population growth. Much of Europe is in this. I also mentioned Russia and Japan. This is characterized by a high affluence and economic development. So these are all developed countries. People here, there's not a lot of poverty in these countries. Everyone has access to healthcare. So these are often countries with socialized medicine systems. So if you need healthcare, you just go to the doctor. It's paid for by the government. You do not have to shell out of pocket. There are fewer young people because the birth rate is low, and there are more elderly. So when you're thinking about how stage 4 relates to an age structure diagram, this would be one of those age structure diagrams that looks more like a kite, that has a large upper population and a narrower base. There are fewer people in the labor force and more retired people, so the tax burden is greater on each worker. And this is actually kind of important right here. Because that middle section of your population pyramid is smaller, there's actually, in post-industrialized countries, a lot of the gross domestic product, the GDP, is actually spent on caring for the elderly, because there's not a lot of workers in that reproductive age segment. It's also one of the reasons why the birth rate is so low. When people are having to work all the time, and a lot of their money is being taken up in taxes to support the elderly, they're not having a lot of children. They don't have a lot of time to do that. Tax burdens tend to be very, very heavy in countries that are in stage 4, that have a high elderly population and a declining population growth. All right, so family planning. Family planning, the definition of that is the regulation of the number or the spacing of offspring through the use of birth control. And as you might imagine, family planning has a big impact on fertility rates. So total fertility rates for women drop dramatically as women are better educated. And I will tell you the number one way to drop fertility rates for women is to give them education. So the answer is why? What is that correlation? Why does the fertility rate drop so greatly when women are educated? Well, many educated and working women delay having children due to the high demands of work and school. So if you're receiving an education, at least, in developed countries, you're not done with your primary education until the age of 18. And if you go on to college, it could be into your mid-20s before you're finished with college. And it is very difficult to balance the demands of motherhood and having a family with going to college. We do know that here in the United States, female students who have families, especially before the age of 18, are at a high risk of dropping out. It's just a very hard thing to do. So as women become more educated and they go into the workforce, they delay having children until they have a spouse in a more stable environment that they can raise children in. A higher age at first reproduction means less children during the lifetime. And again, if women are educated and they're working and they're delaying their first age at childbirth until 25, 26, then the number of years that a woman can have children if their first baby's at 25 or 26 is shortened. If you start having children at the age of 14 or 15, then you have a very, very, very long reproductive life. Let's just say it ends at 45. But if you don't start having children until, 25, 30 years old, then the number of years that you could possibly have children is shortened. Additionally, women with education and with their own money from work have more knowledge about birth control and their own money to buy it. So they're more likely to interact with their partners as equals. This is a big deal. In a lot of developing countries, women who do not work are dependent upon the money that is given to them by the males in their life, whether that's their brother or their husband or their uncle, someone who's giving them money to buy the things that they need. If the husband does not feel that he wants his wife to have birth control, and she does not work and have her own money to purchase that, then she's not going to get birth control. And this happens quite a bit actually in a lot of developing nations. There's a high demand for lots of children, and in some countries specifically male children. So if the woman or the wife is not producing male heirs, the man will deny the woman access to birth control until either the number of children that he wants is produced or a male is produced. And childbirth is just, let's be honest, pregnancy and childbirth for women is risky. It's risky for the health, especially in areas that don't have access to modern medical care. Women die in childbirth around the world all the time. It's a very, very common thing to lose a female in childbirth. And frankly, especially if this is a female who has started giving birth when she was very young, adolescents who give birth are at much higher risk for birth complications because their own bodies are not finished developing. So, having your own money and your own access to birth control because you can purchase things on your own is a huge step towards reducing total fertility rate. So what does this all have to do with the environment? Well, you guys know that the more people there are on the planet, the greater the human impact on the environment. The number one cause of the loss of biodiversity is habitat loss. Well, why is habitat being lost? Well, because there's more humans. If there's more humans, there's going to be less land for wildlife. As we turn wild spaces into spaces for humans, the wildlife is losing their habitat. So more of us, less of them. Also, as countries modernize, they become more affluent. That means that they basically are richer. They have more money. With more money comes more goods and more property. As people demand more stuff, and I'm just going to use that very loosely, whatever that stuff may be, it could be cars, it could be meat. Meat consumption goes up as countries modernize. Whatever that happens to be, their ecological footprint which is how much of the planet's resources they consume, that ecological footprint increases. So if we have more countries with higher ecological footprints, we're going to have less space for wildlife and more impact on the environment. The total environmental impact of humans is hard to quantify. We know that pretty much every ecosystem on Earth has been touched by humans and shows the marks of human intervention. But the total impact is hard to, like, when I say quantify, I mean put into numbers. Estimates can be made, but conceptually there are three major factors that influence human environmental impact. And those are the population, what's the size of the human population, affluence, meaning how rich it is, which of course we know that increasing affluence leads to an increasing ecological footprint, and their level of technology or their level of technological advancement. The higher a society is in terms of technological advancement, the greater impact it has. So this leads to something that we call the IPAT equation. The impact equals the population times the affluence times the level of technology. And in general, as these three factors increase, population, affluence, and technology, the environmental impact of a society also increases. So let's say you have a country that the population is actually declining. So that would bring down your overall impact, but their affluence may still be increasing and their level of technological sophistication may also be increasing. So that would offset the population decline. And because they're multiplied, as one goes up, if the other one goes down, or it's kind of a matter of a balance there. But in general, the more people, the richer they are, and the more access to technology, the greater the impact. So the Millenium Ecosystem Assessment. This was completed in 2005 on behalf of the United Nations. Obviously, 2000 was the millennium, and the United Nations commissioned a study to find out what was the human population, the impact of the human population on ecosystem services. So when I say ecosystem services, we're talking stuff like clean water, the availability of forest products like timber, and anything else that comes from a forest environment, and natural resources. They were also tasked with coming up with a blueprint for sustainable development. We started this course with an idea of what is sustainability and sustainable development. So the Millennium Ecosystem Assessment talked about what is the impact, and then how can we move forward in a sustainable way. The overall conclusion was that human demand for food, water, lumber, fiber, and fuel has led to very, very large and irreversible loss in biodiversity. I've talked to you about the sixth mass extinction, that most environmental scientists believe that we're in the midst of a sixth mass extinction. We're losing species at a high rate. This is an irreversible thing. Once the species are gone, they don't come back. Obviously, if humans go away, there'll be a change in biodiversity as well. But once we lose a species, that species is gone forever. We have so impacted most of the naturally functioning ecosystems on the planet that biodiversity has been impacted in an irreversible way. So a quote from the Millennium Ecosystem Assessment read, "Human actions are depleting Earth's natural capital, putting such a strain on the environment that the ability of the planet's ecosystems to sustain future generations can no longer be taken for granted." So one of the things that we studied before we talked about human impact was, what do ecosystems function like normally? And we talked about trophic cascades, and we talked about feedback loops, both positive and negative, and the fact that ecosystems, just like bodily systems, tend towards equilibrium, tend towards homeostasis unless they're disrupted. Well, humans are a very disrupting force on ecosystems. So at the end of the day, ecosystems provide services for humans, and they have to function correctly in order to provide those services. So the ability to filter our water, to regulate our climate, and the ability to absorb our wastes, all those things are ecosystem services. If we damage the very way that ecosystems function, and this is going to lead into our next concept, which is biogeochemical cycles. If we damage the cycles, the natural cycles that keep our environment in homeostasis, we literally are imperiling our very existence on this planet. And so that's our lead in to biogeochem. Thanks, guys. Talk to you later.